we're just going to start it off with a third example. Draw a free body diagram for the refrigerator pictured below. Here's something before, like I'm going to let you guys, well, I mean, you can pause it, but before you try and do this one, maybe if you're going to try and do it on your own, know that normal forces always are perpendicular to the supporting surface. So if you draw this free body diagram, first you're going to have to draw the refrigerator in the same orientation that it is, and it's slightly tilted. And then the normal forces that are keeping the object from going through the ramp are perpendicular to the surface of the ramp. So the normal forces would go up that way. So if you want, you can try and pause it and just draw a free body diagram. What I'm going to do is I'm going to just do it because you could have already paused it. So, well, first I'll draw my refrigerator as just a box. I'll say, okay, there's my refrigerator, still at an angle. That's weird. So I have my refrigerator, and the normal force I just got done telling you is pushing up against the refrigerator, perpendicular to the supporting surface, and the supporting surface in this case is the ramp. So the normal force, I'm going to say, is going up this way. So that's the normal force. That's the supporting force. It's allowing it not to fall through the ramp. And then the weight, this is tricky. The weight of the fridge is not, I mean, the gravity is pulling down the fridge. That's what causes the weight. Weight is the acceleration due to gravity, right, or something like that. So the weight is not caused by the ramp, it's caused by the earth, and the ramp is on the earth. So like when you draw the force, the weight, the force of the weight, that has to be going straight down because I mean the ramp is on earth. So that's going straight down. So we'll say that's the weight of the fridge, and it's at some angle. We don't know what that angle is, but it's at some angle. It's not, directly perpendicular with the fridge. So that's some angle theta. You don't really have to write that because we don't know what it is. But, in other calculations you might have to, in like physics or something. Okay, so we have that. We got this person pushing on it, it looks like. So there's an applied force. You could draw it over here. I'm going to draw it this way. Maybe it's sliding up the ramp. So I'll draw that kind of big. That's the applied force of the guy pushing on the fridge. And, well, there's friction. And that's parallel with the ramp. There's the force of friction. If I make the friction smaller than the applied force, then that means the fridge is moving that way. If I make the friction equal to the applied force, it means it's not moving at all. So this is the force due to friction. And there you go. That's your free body diagram for that fridge. Isn't it beautiful? It's a beauty, ain't it? All right. Let's move on. Sometimes you'll have a system of objects and forces acting upon those objects, and we can actually separate all of that. I mean, this is also a system of objects and stuff. I mean, there's a person, there's forces acting on the person, just as there's forces acting on the refrigerator. So let's take a look, example 4, let's take a look at a system of like a pulleys and stuff, okay? So here we've got a pulley system where there's the support. This is the support. This is one pulley. This is a fixed pulley. This is a movable pulley. This is mass 1. No, sorry, mass 2, and then this is mass 1. So it says create a free body diagram for the pulley system pictured below. Pictured? What? That's not pictured. Oh, that's a U. Pictured below. All right. So let's just start at mass 1. To do this, we're going to assume that the lines that are going through here, that line that wraps around and goes up there, we're going to assume that those are weightless and that these are frictionless pulleys. So the only forces that we're going to account for are the the forces due to the weight of the masses, and also the tension in the pulleys, or tension in the rope or string or whatever. So the free body diagram for the mass of the first weight, well, we isolate it, remember? And we have well, it's not a normal force anymore, it's a tension force. So that's interesting. So we'll call that the force of tension in the string, and then if it's not moving at all, we'll draw those forces equally opposing each other, and this will be the weight of the force due to gravity, the weight of mass 1. So that's simple. Let's say weight 1. So that's for the free body diagram for the first mass. Next is the free body diagram for the fixed pulley. That looks like so. And what do we have? We have a support going from here to here. There's tension in this. So this, I would say, that's some kind of tension for the pulley. But we also have the string going down through there. That, well, maybe I should call this force of support. I'll call that. That's the force of the support for the pulley. But we do have tension in the string, and that's the same actually as the tension in the string or the rope throughout the whole entire system. So this F of T, those are equal if nothing's moving, and it's equal to that because it's the same string. Those two things are the same, right? This and that are the same. They're the same string. But it's also the same string over here and the same string over there. So if we did, we could do the mass 2 in the same way we did mass 1. It would just be the tension and the weight of mass 2. And then also for the free body diagram for the movable pulley is just the same as this, except for in the opposite direction, right? If you want to pause it, you can try drawing that, but it's really simple, right? You just have the pulley, you have the weight of mass 1, right? That's, I can just say weight of, mass 2. And then we have Ft, that's the tension, and the tension is the same throughout the entire system because it's the same rope. That'd be weird if you had different tensions on different spots. Because it's all the same rope. Hopefully that makes sense to you. I guess actually this is, the pulley has some weight. If we considered the pulley to be weightless, then it would just be the weight of mass 2. But if the pulley wasn't weightless, then this would be plus the pulley weight. But I'm going to ignore that for right now. So there we have it. The free body diagrams for all that stuff. Cool. Eventually, we'll get to building trusses, which is kind of cool, but there's also some complicated calculations that we need to do. I don't know if we'll get to do this over break, before break or not, but we'll have tension forces. That's like when there's a pulling, it's just under tension, and then compression forces when they're like pushing inward on like a beam or something. And we'll have to distinguish between those two. But for right now, for pulleys or something that's hanging, like a support that's hanging something, like you hang a sign or you hang a street light or something like that, those are going to be tension forces. And that's all for free body diagrams for now, kids. Have a go away.